Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. Let's jump into it because last time we were doing somewhat of an information dump, and that's going to continue for this class. So let's get that. Okay, so make sure I can see the chat here. So as we discovered last time, sometimes we can take derivatives repeatedly. We can take them over and over. That's the notation that we can use for the nth derivative, whether we're using the prime notation or the Leibniz notation. Just keep adding notches in the prime notation until it gets annoying. You write just the number in parentheses as a power. And with the Leibniz notation, you just write d to the n of y over dx to the n for the nth derivative. Now, we're not going to go super high in derivatives, but we do want to talk about the second derivative because it has a lot of important applications for us at this point, such as with the physics of motion. Second derivative would actually give you the acceleration function, which is the function that's telling you whether you're speeding up or slowing down. So knowing where your current position is one thing, knowing how fast you're moving is another thing, but then there's another thing. But wait, there's more. There's also, am I speeding up or slowing down? Yeah, I know how fast I'm moving right now, but 1 second from now, will I be moving faster? That is often a question you want to be able to answer. And so the second derivative answers that question. There are, and these are just things you should actually know. Maybe I should have put those in a box or something, but there are going to be times when you need to know this. When it's not stated in the problem, so you should probably know that. So maybe like 9.8 instead of 9.81, usually won't require 2 decimal places there. The next thing that the second derivative is useful for is for something called concavity. Now we talked about what concavity is, but what you really want to remember is like this mnemonic right here. Concave up like a cup, concave down like a frown. Concavity is about shape. Has nothing to do with whether you're moving up or down, has nothing to do with whether your function is positive or negative. It has everything to do with how your function is shaped while it's doing what it's doing. So it's shaped like a smiley face, it's concave up. Shaped like a frowny face, concave down. You can identify when it hits one of these properties with the second derivative. So it's concave up if the second derivative is positive, and it's concave down if the second derivative is negative. So yeah, so that's what you want to know there. We also spoke about inflection points. Now, inflection point is a point where you switch concavity. So on one side of the inflection, you are one kind of concavity, and on the other side, you're another kind of concavity. And we just kind of verbally went over some examples why knowing what the concavity is and knowing when it changed is going to be important. We looked at 2 examples, but the idea is if you're increasing and you're concave down, what it means is that you're increasing, but you're at a slower rate. But if you're increasing and you're concave up, you're increasing at a faster rate. And if you make it like you're decreasing, then the opposite is true, right? So if you're decreasing concave down, it means you're decreasing at an increasing rate, like you're decreasing more and more over time. Whereas if you're decreasing and you're concave up, it means you're decreasing at a decreasing rate, which means that the amount you're decreasing by is getting smaller, etc. And sometimes knowing that kind of level of thought is important. Now, we know these are important, or at least I'm telling you they're important for this class. So just like, let's say you know this is important, whether or not you believe it's actually important in real life, it's going to be important in this class. So now the idea is, okay, so we know the derivative is important and the second derivative is important and that it can tell us all these things, but exactly how does it tell us all these things? How do we actually put this all together and figure out where these things happen, like at the end of the day? You give me a function, I want to examine it in terms of concavity and increasing and decreasing and all that stuff. What do I actually do? And so that leads us to the important test, which is what we're going to talk about now. The first derivative test and the concavity test. As I mentioned, there is a second derivative test, but for us, it's going to be superfluous because all the information we can get from there, we can get it from the first derivative test and more. And I'm going to be asking you to do the first derivative test anyway. So kind of doing the second derivative test is kind of pointless. So we're going to talk about these 2 tests, how they actually work, what they can tell you, and talk about the derivative a little bit more after that. And in terms of what do I want to tell you? The existence of derivatives after that. And then we'll kind of go back to more computational stuff, like specifically actually learning how to compute derivatives without having to go through the limit definition, because sometimes that's super annoying, especially if you have certain kinds of functions. There's no reason to go through the limit definition. So that's what we'll start next class, I think, is when that gets started. But let's actually continue. So let's talk about the first derivative test. Okay, what is the first derivative test? Well, what does it tell us about? Increasing, decreasing, maximums, minimums, right? So if you're interested in, oh, is my function moving up as I go from left to right? Is it moving down as I go from left to right? Did it hit a maximum point? Or did it hit a minimum point? Or something like this? Or something like that, right? Did something like that happen, right? Like a max or a min or a max or a min, right? Or is it increasing or decreasing? Right? These are the kinds of things you want to find out about. Now, if this is what you want to find out about, one way you can do that, which is a very nice way to do that, is what's called the first derivative test. So let's actually talk about how we actually do that. Well, step one, you would find f prime. And I want to combine this in step one. The critical points. Let me just mention here, a critical point is a point where f prime equals 0 or f prime is undefined. So you're going to find the derivative, then you're going to figure out where's the derivative 0, where is it undefined. We call these guys critical points. Okay, so that's actually step one. Okay, now step two, you don't necessarily have to do it like this, but I think this is the best way to do it. So you're now going to examine all of the critical points that you found in earlier. Plot the critical points, critical x values found above on a number line. Values. So you're going to have a number line where it's just nice to have like a visible representation. Notice here, label that number line that is the derivative, because there are a couple of situations in which we are going to use number lines. So it'd be nice to label this number line by the derivative so you know which number line, what this number line represents. Okay, so let's say you have a critical point. Like you found some x value here, and this is a critical point. Okay, so you plot that on the number line. What you're going to do at that point is you are going to pick a random number on either side. So let's say there's x naught, and here I have x1. Pick numbers on either side of each critical point. Here, x naught and x1. Make sure you do this in between each critical point. So you don't want to put like something far to the left of a critical point, but there's like 5 critical points in a row and you only pick one guy to the left of all of them. It doesn't work. You need to pick a left and a right around each one, right? Do this between each critical point. So if you had, two critical points, let's say you have x1, this is critical point 1, and you have another one, x2, this is critical point 2, then you should be picking at least 3 numbers here. You're going to pick over here, like, an x3. You're going to pick in between here and x4. You're going to pick over here and x5, right? You want to be on either side of each individual critical point, right? So you would need to check the x4, for example. It's not good enough to have the x3 and the x5 because the x3 is on the left and the x5 is on the right of each of them. You need a left and right value on each critical point, right? So that's important. Test these new values in the first derivative. Okay. So this, and for the most part, these values are completely random, right? So they're not particular values you would have, right? So this is just some random number to the left and some random number to the right. Right? So you are going to find your derivative. You're going to figure out all the x values that make your derivative 0 or undefined. Then you're going to plot those on a number line. You're then going to pick random numbers in between each of these critical points, one guy on the left, one guy on the right, right? And you are going to test them in the first derivative, meaning you're going to plug in the x0 into the first derivative. You're going to plug in the x1 into the first derivative. And that leads us to the final step, step 3. Conclude based on the following. So here's one scenario, is you are going to, need to show you where it's increasing and decreasing. Versus this. So let's say here I have a critical point. And here I have a critical point. So like I said, we're going to pick a random number over here, x0. Pick a random number over here, x1. What I'm going to do is I'm going to plug in that number, that random number that I picked, into the first derivative. Right, this is the first derivative test. Okay, and I'm going to plug in this number into the first derivative. So again, if I have the number over here, I'm going to plug it into the first derivative. If I have that number over here, I'm going to plug it into the first derivative. Now, something is going to happen. Remember, the red x is where the derivative is 0 or undefined, which means to the immediate left and right of it, the derivative is not going to be 0. So it's going to either be positive or negative. And based on that, you're going to be able to tell certain things. So here, let's say on the left of the first one, do I want to do these separately? Don't want to confuse you, like these are right beside each other. These are two, I'm showing you two different scenarios that can occur. Okay, so here's one scenario. You plug in that number that you picked at random into the first derivative, and let's say you got a positive number. What that means is, well, we know what that means. Positive means you're increasing. It means that this side of your graph, you're going up as you go from left to right. Then let's say over here, you get a negative number. Then this side of your graph, you're going down as you go from left to right. And then you can conclude if f is continuous at x, and that part is important. If it's continuous there, like the value is actually filled in, it's actually on your graph, then we have a maximum, right? You're increasing before that, so you're growing until you hit that red X, but then immediately after that, you start decreasing. You're falling from that X. What it means is that that X was the highest point in that region. So in that local region, you increase to it, and then you start decreasing right after you hit it, right? So if that point is actually on your graph, it's not a hole or there's no asymptote or anything, you can conclude, hey, that critical point represents a maximum point. Like that X value is going to give me where the maximum is. Now, of course, otherwise, you can see where it's increasing or decreasing just by seeing the sign of the derivative. So I know it's increasing on the left of this part. I know it's decreasing on the right. I can tell you where it's increasing and decreasing. From negative infinity up to this X, it's increasing. Then from X to positive infinity, after that X, it's decreasing. I can tell you that information, but I can also get the information of a max or a min. So knowing about increasing or decreasing can also tell me about max or min consequently. But the opposite scenario could have happened. I could have gotten a negative on this side and a positive on that side. In which case, that means I'm decreasing here towards the X and increasing there as I leave the X. Of course, that means you hit a minimum provided that the function is continuous at that X value. So if f is continuous at that X, then we have a minimum. Right? If it's not continuous, you have nothing. Otherwise, including if f is not continuous at x, we do not have a max or min. But we can still identify increasing and decreasing. Right? You'll always at minimum get increasing, decreasing data from doing the first derivative test. As for whether or not there are maximums or minimums, it's possible that your function doesn't have one of them. And so you wouldn't actually find them here. So what could happen is if, so maybe I can talk about some examples. Example, let's say you have your X right here and you have like increasing and increasing, then it's neither a max or a min, it's nothing, right? Or if you have this here and you're decreasing and decreasing, then it's neither a max or a min. Or you have this here and you have X here, but your f of X is undefined, and you have this and that, then it's also nothing, right? So for none of these, you have neither maxes or min, neither max or min occur, right? So these are the two patterns you're looking for, a maximum or minimum. Increase on the left, decreasing on the right. Potentially it's a maximum if your function is continuous at the point. If you're decreasing on the left, increasing on the right, then potentially it's a minimum if your function is continuous at the point. If your function is not continuous at the point, or you do not see one of these patterns, like you see some other pattern, then it's neither. And you can only get increasing or decreasing information from it. That's pretty much the first derivative test, right? So you find the critical points, essentially, which means you find the derivative. You figure out where it's zero and undefined, which means you're going to end up solving equations. You're going to plot the critical numbers on a number line, and then you're going to test them and conclude based on the sign of the derivative and whether or not you're continuous at the point of consideration. Right? So yeah, that's the first derivative test. Now we're not going to actually use it right away. There's going to come a point later in the semester where we're going to use it. But at this point, I'm just giving you information about the derivative. So I'll just tell you it at this point. Let's talk about the concavity test. Okay. So here, what color did I put down? Oh. Here it tells us about where something is concave up. Tells us about concavity, concave up versus concave down. And inflections, if any. Right? So when you know that that's what you're interested in, you don't care about whether it's increasing or decreasing. You don't care about whether it's a max or a min. You don't care about whether the function is positive or negative. What you care about is the shape. And if there are any inflection points, then that's when you use this test. So it's very similar. So step one. So yeah, this is like whether we're concave up or concave down, or if an inflection happened. Right, so all of these scenarios is what you're after here. Step one, you're going to find f double prime and its critical values. Which means, f double prime equals 0 or undefined. Step two, again, you're going to plug these on a number line. Now, within the same problem, you might have to do both of these tests. So what I would do is I would actually, again, I would label this f double prime so I know which one I'm looking at. And so let's say here's an x value with f double prime of x equals 0 or f double prime of x undefined. and I'm going to pick a random number over here and another random number over here on either side. I guess I could fill that in. I mean, at this point it was clear, but we can fill that in here. F prime of x equals 0, or f prime of x undefined. That's what critical point means there. But here, critical point means the second derivative, right? Because we're looking into concavity, right? So step 3 is you make your conclusion. Conclude based on a couple scenarios. So one, you can have your critical point here. So here is where your f double prime equals 0 or undefined. You can pick a random number over here. And let's say you got that the second derivative at x naught is positive. What that means is you're shaped like a smiley face. So I would kind of do that kind of shape, not to confuse myself with it moving up or anything. Just make a smiley face so I know that's the shape. Over here, let's say I found that my f double prime is negative. That means it should be a frowny face, right? And then you can conclude if f is continuous at x, then we have an inflection. How do I know? Well, it switched concavity, didn't it? It was concave. It was concave. It was concave up over here, and then it's concave down over here. It made a switch. By definition, if that point is on the graph, it just went through an inflection point. Or, of course, could have gone the other way. Here's my guy x, where the second derivative is 0 or undefined. So I pick a random number over here, and the second derivative of that number gave me something less than 0, which means it's concave down. Pick a random number over here. Let's say the second derivative gave me something greater than 0, which means it's concave up. Means over here, I'm shaped like a frowny face. Here, I'm shaped like a smiley face. And of course, if f is continuous at x, then we have an inflection. Otherwise, there is no inflection. But we can still determine concavity. Okay. So that is the concavity test. Pretty similar to the first derivative test, except when you have positive and negative, you have a different interpretation of it. So in the first derivative test, you'd find the critical point, find the first derivative, set it equal to 0 undefined, solve for the exercises that make that, plot them on a number line, pick random guys in between them. Plug those guys into the first derivative. Whether you get positive or negative, positive means it's going up, increasing, negative means it's going down. And if you're continuous at a point and you went up before and down after, then that point is a maximum. If you're continuous at a point and you went down before and up after, that point is a minimum. In any other scenario, it's not a maximum or a minimum. Concavity test is you kind of do essentially the same thing, but with the second derivative. Find the second derivative, figure out where it's positive, where it's equal to 0 or undefined, plot those guys on number line, pick random numbers in between them, plug them into the second derivative. If you get positive, it means you're concave up. If you get negative, it means you're concave down. If you switch from concave up to concave down, or you switch from concave down to concave up, you have an inflection if the point is continuous, if you're continuous at the point. In any other scenario, you do not have an inflection. But of course, you can still talk about where the concavity is. Oh, on this interval, it's concave up. On that interval, it's concave down. You still be able to tell that. You just you won't have an inflection of which to speak. So yeah, so that is the process by which you can figure out the important information that we've decided was important last time. At this point, I guess we can do a summary. Kind of tie this all together. Let's look at a function. Let's look at what this function tells us. Let's look at how it tells us. So let's look at the original function, right? F of x. Very familiar function. We've been friends with this guy for a long time. We go way back. What does he tell us about? Well, he tells us about location, position, points on the graph. Right? Current state. Right? That's what that guy tells us, right? How does that tell us? Well, by evaluation. Plug in x, solve for y. Don't want to say solve for y, too strong word, compute y. You get x comma y, which is your position, location, etc. Right? That's how we do it. But that's not new to us. That we've been doing forever at this point, right? Evaluate a function. The function is telling you some current state. You can figure out what that state is just by plugging in an input, finding the corresponding output. Whenever we're at this point, this is the result of being at that point. Now, in Calc 1, we've introduced what's called the first derivative. Now, what can the first derivative tell us about? Well, it can tell us about when a function is increasing, decreasing. It can tell us whether they're about maximums or minimums, if they exist. How does it tell us? First derivative test. That's the process you would go through to figure it out. By going through the first derivative test, you'll be able to figure out all that information. Then we looked at f double prime. What does that tell us about? Well, it tells us about concavity. Concave up versus concave down, and inflections, if they exist. How does that tell us? Concavity test. So this is a summary of all the functions and when we want to use them. So you don't just use any of these functions for any random old reason, right? If you're looking for a position or a current state or a point on a graph, you do not look at the first derivative. You do not look at the second derivative. You look at the original function. If you want to know how fast something is moving, is it increasing or decreasing? Are there any maximums or minimums? You look at the first derivative. You do not look at the original function. You do not look at the second derivative. And if you want to find, is there an inflection point? What's the concavity? How am I shaped? Is it concave up or concave down? You would look at the second derivative. You would not look at the original function. You would not look at the first derivative. So for example, if I were to ask you, identify the maximum or minimum point of this function, what you would do is you would start with the first derivative. You would use the first derivative in the first derivative test to find all the x values that give you the maximum x value. Now, to find the maximum position, which is what I asked you for, you're going to take those x's that you got, and then you're going to go back to the original function. You're going to plug them in, and that's how you're going to get the location. What you want at any given time is going to dictate which of these functions you use. Whenever you're finding a location, use the original function. Increasing, decreasing, max or min, use the first derivative. Concave up, concave down inflection, use the second derivative. Do not mix up who you should be using when, because that's it's a rookie mistake. Don't do it. Right? So that's kind of the functions and when we should use them, what we should use them for, what can they tell us, and how do they tell us, right? So that's very useful to know. And we're going to see applications where we have to put that all together pretty soon. Not now, but just these are just some important ideas to know now, so that when we need them later, we'll be able to pull on them. There is something though that I do want to actually cover here. Is this the last conceptual thing? Yeah. There is something that I do want to cover, and I want to talk about the existence of the derivative. Okay. So derivatives are important, but don't forget, derivatives are limits. And we know that sometimes limits don't exist, which means there's no reason to think that the derivative is always going to exist. It's possible that I try to find a derivative, but there just isn't one, right? So let's actually talk about that. How to know if there may not be a derivative. So derivatives are important, but they are limits. They don't always have to exist. How do we know when a derivative would exist, that I should even be searching for one? Well, I think it's going to be easier to identify. Well, to answer in the affirmative, I can tell you what the answer is in the affirmative. But it's going to be too vague to take action on. But this is really what the answer is. The derivative exists at a point on a function f if f is approximately linear at that point. What does it mean to be approximately linear? It means it might not look like a straight line, but if you zoom in more and more and more, it starts to look more and more and more like a straight line, i.e., looks like a straight line as we zoom in more and more, right? So it might look like some kind of curve, but you kind of have the idea that if I were to zoom in and max and start, increasing the magnification, it starts to kind of flatten out as I do that, right? Once a function actually does that, the derivative is going to exist there. It may be difficult to find, but it's definitely there somewhere. But that's hard to act on. So let's answer an easier thing to identify. When does it not exist? Okay. So this is a much easier thing to answer, and it's a thing that you can identify even quicker. There are three main things that you will actually stop a derivative from existing. One, f of x is not continuous at x, right? That's the first thing. So if you have a function like this, or you have a function like this, right? There is no derivative at a. You don't even waste your time looking for one. So if your function is not continuous, you can't find a derivative. You can't solve the rate problem, right? Which is why continuity was important, why we went through it. And why is that messing things up? Well, because of the affirmative answer. How much do you have to zoom in so that a hole starts to look like a line? It's never going to happen. It will never look like a line, no matter how much I zoom in. There's a hole there. There's a gap, right? There's a jump. No matter how much I zoom in on this empty space, it's never going to look like a line, right? So discontinuity actually messes things up for us. So we can know for a function, wherever that function is undefined or not continuous, the limit doesn't exist, the derivative itself is also not going to be there. So if I look at the function y equals 1 over x, I can automatically know that when x equals 0, there is no derivative. Why? Because the function itself is discontinuous at 0. So if someone asks me, what's the derivative of 0? Like, that's a useless question. That the answer is there is none, right? So that's one situation. The second situation is at sharp corners or cusps. So if you have something like this, or this, or that, or anything of that sort, right? Like boom, 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 no derivative at the red points. Because it's a sharp corner. Why is there no derivative at the red points? Well, for a derivative to be there, I have to be able to draw a tangent line. For me to be able to draw a tangent line means that when I zoom in, the thing should start to flatten out to look like a line that I can fit a tangent line to. How much do I have to zoom in so that a sharp corner starts to look like a flat line? It'll never look like a flat line. It's a sharp corner, right? No matter how much I zoom in, there's just going to be one point. There is going to be, in fact, an infinite number of lines that I can draw through that point that just as well approximates that point as just as good compared to any other one, because literally the only thing that's there is one point. There's nothing else beside it. There's no defined tangent line. There's no one slope that is going to work, right? So yeah, at sharp corners. And there's a common example here is y equals the absolute value of x at x equals 0. It has no derivative there, even though it's continuous. So we know this graph. We've known him for a long time as well, go way back. Turns out, no derivative at the origin. Right? Because it's a sharp corner. And like, there's no derivative. Fight me, right? You're like, okay, you don't believe me? Well, let's find the derivative at 0. What that would mean is I'm taking the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. Well, that is going to be the limit as h approaches 0 of absolute value of 0 plus h minus absolute value of 0 over h. This is going to be, stay still, limit as h approaches 0 of absolute value of h over h. And we actually saw that this does not exist. We saw this in a previous example. I did it long ago, and I said that eventually we're going to come back and I'm going to show you why this particular limit was important to us, where we did the absolute value x over x as x approaches 0, and we looked at from the right and from the left. I don't know if you remember that. And we saw that the graph of this guy looks like that. And then we determined that the limit does not exist. But in this case, that limit happens to be the limit for the derivative of the absolute value function at the origin. Turns out it does not exist. There is no derivative there, right? So that's a formulaic example. But if you can look at the picture and determine, hey, there's a sharp corner, there's no derivative there either. And there's one, which is a kind of weird one. The tangent line would be vertical. So we know that vertical lines have no slope. And we also know technically that for an individual x value, you can have more than one y value. So you're never going to have a function that's completely vertical the whole time. It wouldn't be a function by definition. However, there are these weird functions who they go vertical for literally a split second, for like 1 point, right? So they'll do something like, right? And they go vertical at this point, and then they're like, right? And the thing is, if you zoom into that point, it will eventually start to look flat like a line, like there would be a tangent line passing through here. Just by how it's shaped, it's curved down very, very subtly and then shoots off like that, to the point where when you start to zoom in, the best line that it starts to look like is going to be a vertical one. So it's a vertical tangent line. And here, no derivative. Since this is kind of a technicality, vertical lines have no slope. Hence, they have no derivative. That is it. So that was a lot of information dump, but it's important information dump. Exposition. It's like when you're watching a movie and then the narrator comes on the background and just starts telling you all this stuff. Why is he telling me all this stuff? Well, you'll see as the story unfolds why he was telling you all that stuff. But yeah, this was important stuff for us to know. What would make a derivative not exist, as well as what are the different derivatives and when and how can we use them? Very important. Knowing the second derivative test, the first, well, not the second derivative test, knowing the first derivative test and the concavity test. The second derivative test, once you do the first derivative test, is useless. So yeah, so this is how the first derivative test works. That's how the concavity test works. That's just a summary of knowing which function does what. And these are when the derivative will not exist. When its function is undefined, at a sharp corner, or if your function does this kind of weird behavior, weird inflection behavior, where the best tangent line is a vertical line. So by definition, it has no slope, hence no derivative. We'll stop there. Next time should be pretty fun. We'll go back to the computational kinds of things. I'm going to give you some shortcuts, some formulas, some things that can allow us to take derivatives easier. But for now, that's where we're going to end it. So hopefully understood. Hopefully that went well. That's it. TGIF, enjoy the rest of your Friday. Enjoy your weekend. And I will see you guys on the next one.